All right, let's get started. We were talking before class. I walked in and said, "Oh, that's what you all look like." Given the fact that our mask mandates and whatnot have been lifted. Okay, a little bit on logistics. So attendance grades are up to date. Still working on the exam too. That's going to take a little bit. Just so you know, my target is next Tuesday for the second exam. There is no homework due today. Okay, so the homework that was assigned is actually not due until Thursday, and it will definitely become clearer how to do that assignment after what we do today. What I will tell you is that what we do today, I think, is more challenging than the homework. If you can do what we do today, no problem. And I have a little picture here of some alphabet soup because I do want you to be prepared for that. We are going to have some alphabet soup today, okay? Because we're going to be doing some symbolics and some derivations and whatnot together. It's very procedural and it's very step-by-step, but I want you to sort of get ready for that, okay? So with that, let's get right into it and let's talk about beam deflections. Hopefully everybody watched the video, the lecture that I pre-recorded in advance for a lecture today. I tried to keep it pretty short, but the idea is that, what the whole point of that lecture was really to sort of get at this right here. The second derivative of deflection being m over EI. And that is it's sometimes called Euler-Bernoulli beam bending theory, sometimes it's called moment curvature. But that differential equation that defines deflection of a beam is one of the most fundamental equations in all of engineering mechanics. I would argue it's among the simplest but most necessary differential equations that is solved by students in engineering. Okay, so if you ever wonder, why the heck do I take Math 335? It's because we deal with problems like this. Okay? Now, there are ways to solve this problem, and there are different techniques for solving this differential equation. In fact, I'm going to show you one method using direct integration, and for those of you that take me for structural analysis next semester, we'll use another method. That's a little bit, has a little bit more steps, but it's a little bit robust. But then again, that's more of a critical element for civil engineers anyways. And so basically what we do is we say, well, is m over EI. I'll just integrate twice to get the deflection. That's basically it. Now, these are indefinite integrals, right? So whenever you integrate some function, right, what is the result? It is some other function plus c, right? There's an arbitrary constant of integration, okay? Well, where we are integrating twice, there are two arbitrary constants of integration. So we'll call those C1, C2. So if you ever heard plus C doesn't matter, well, it matters here, okay? Now, the way that we're going to solve for those unknown constants is through boundary conditions. And boundary conditions basically refer to conditions for the structure, okay? So in applied physics conditions that we use when we're solving for unknown constants and unknown components of differential equations. And those are boundary conditions and initial conditions. So initial conditions would be like in Physics 211, you have a projectile motion problem, and at time t equals 0, you have an initial position and initial velocity. Those are initial conditions, right? So those are initial conditions as a function, and they're more related to what's going on at an initial time. Whereas boundary conditions are what's going on in regards to a specific position, okay? So boundary conditions are really as a function of x. Now, I'm belaboring the math side of things, but really the physics and the mechanics side of things is really easy, right? If I have a simple support, I know that the deflection equals 0 at that support, either being a pin support or a roller support. So I can plug in x equals 0, set the equation equals 0, and solve for a constant. And so for simple supports, we have that the deflection equals 0. For fixed supports, deflection equals 0, but the first derivative of the deflection equals 0, because it's not only a point where we have 0 deflection, but we have 0 slope as well. Okay, so we're going to have two problems: a cantilevered beam and a simply supported beam, and see how that works out. Now, the last thing that I'll point out, and I think we'll be able to get right to this, is our unit conversions. In USCS units, we have a typical unit system that we use for beam deflection. here in a second. But the idea is that, when we look at structural problems, for example, we tend to express our member lengths in feet, but our section properties and our material properties in inches. So, for example, the modulus of elasticity might be KSI or PSI, and then the moments of inertia might be inches to the fourth, as opposed to feet to the fourth. Now, there's sort of two ways of handling that. The first is you can convert all of your inputs to a consistent unit system. There's no reason that you can't do that, and that'll work. Or you can plug everything in using your typical units and derive a conversion factor. And so for deflections, the conversion factor is 1728. The reason for the 1728 is if you follow everything out, if you convert a foot 3 times, and so 12 times 12 is 144, times another 12 is 1728. And for deflections, it would be 1728. For rotations, it would be 144. But with rotations in beamland tend to be very small, and it is very advantageous to express those in degrees. So we throw a 180 over pi in there to get them in usable units of degrees. And so that's how it works for US units. For SI units, it's actually going to be a lot simpler, because ultimately what you're going to be doing is converting meters to millimeters. So instead of like 1728 or 144, instead of you can also convert to consistent inputs, and then it works just as fine. Okay, now I want to be clear that one of the most common methods for computing deflections in beams is to just look them up. Okay, there are oodles of beam deflection charts available to you as an engineer. There are some in the back of your textbook. There are some in the FE reference manual. Like, they're all over the place. You can go to Google and search for right now. And typically what you will find is deflections for basic cases. So, for example, here's a simply supported beam with a uniformly distributed load, arguably the most fundamental beam analysis situation that engineers have to deal with. Simply supported beams are just that simple, and all beams must be able to withstand their own self-weight. That's pretty easy to conceptualize that this is a very important case. Typically, what you will find is a function for deflection, or maybe a function for rotation, as well as maximum deflections and rotations. Now, I will go ahead and admit right off the bat, I am being a little interchangeable in my notation. The book can tend to use V for deflection. I'm using Y. The reason that you do that is if you look in mechanics land, you find that X, Y, Z is your coordinate system. So U, V, W is your deflections. And so Y may be the direction and V is the deflection. To me, I just tend to think of things in X and Y when I'm first teaching this. I think it's a little easier for students to sort of latch on to something they're familiar with. So we'll just use X and Y to keep things simple. But for instance, this is the deflection. This would be Y of X. This would be Y prime of X. This would be the rotation. Here's the maximum deflection and the maximum rotation. We're going to be able to derive these today. And then I'm giving you a homework assignment where you're going to derive another one. And the other one that I'm having you derive, again, is simpler than the one we're about to do. Any questions? All right, let's dive right in. I'm going to pull up the notebook. This is already on the notebook as well. But let me go back here. Okay, so here's the problem that I want to look at. I have a beam here that is a simply supported beam subjected to a uniformly distributed load. And I want to derive a function for the slope and deflection shown. And I want to determine the maximum deflection using these data, right? So we have E is 29,000 KSI, 1,500 inches to the fourth, L is 30 feet, and W is 2 kips per foot. So we're going to start out this problem in symbolic land, and then we'll plug and chug at the end. So I say you're get ready, there's going to be a fair amount of symbolic manipulation here. It's not hard. It really isn't. It's actually really easy. You just got to pay attention. The big thing to keep in mind is that X's are variables. Everything else isn't. Recognize that? You're going to be hunky-dory. So I'm going to give you a sec to copy this down, and then we'll get rocking and rolling on this. Give you a little bit? I think I heard a yes on that. Now, as you're drawing this out, as you're writing this out, I want to make some points. Okay, so we're going to be deriving a function for deflection and a function for slope. Those functions are going to be defined with respect to the coordinate system indicated, right? So, what is x right here? Right here. 0. What is x right here? L. Okay. What's x in the middle? L over 2. There we go. Okay. Just making sure everybody. Okay. And so, if we look at this, we can probably start to think about what our boundary conditions are going to be. It's not very difficult. You just need to take your time with it. Okay. Are we good here? Now, so ultimately, let's sort of look at our approach. So our approach is going to be trying to solve this differential equation. Okay? All right, this is going to be the differential equation that we solve. Now we're going to treat EI as a constant, so I'm going to move the EI over here and set up the problem like this. So what that means is I'll have EI times the second derivative of deflection equals moment. And then what I'm going to do is integrate that moment twice. But the big question that we have to answer first is, what the heck is moment? What is M? Okay? So that should be the first step in any deflection problem, is we have to know what we're going to integrate. Okay? And it's not just M, it is a function. Okay? So let's look at that. So I'll say, we can sort of call it step 1 if you want, it doesn't really matter. But we can say step 1, determine M of x, our moment function. Now, before we start chugging away at things, let's use a little bit of common sense and make sure that the answer that we get jives with what we think it should look like. Okay? Now, what I mean by determine M of x, what is M of x? I'll say note, M of x once plotted is what? What do you think, if I plot M of x, what do you think it's going to look like? Well, what would I call that plot? It's the moment diagram. Moment. Get ahead of myself. That's what M is. It's the moment diagram. Okay? So let's look at what the moment diagram, let's conceptualize. What is the moment diagram going to look like for this problem? I already heard somebody say the magic word, but let's follow it out. So here's the beam. It has a distributed load. Right? It's got reactions right here. So what does the shear diagram look like? I jump up. I linearly decrease down. Jump up. That's the shear diagram. And so the moment diagram, I lot to a little to a lot. That's the moment diagram. So without doing any derivation, any formulas, any equations, anything like that, what do I know about the moment function? So I know M of x is parabolic, i.e. quadratic. I know that M of x opens downward. So that means that the x squared term is negative. right? Does that make sense? It's a downward parabola. So the x squared term in whatever function I generate has to be negative. With me so far? Okay. Any questions on that? Now, so m of x, once plotted as the moment diagram, what does that mean? That means that is telling me the internal moment in the beam at some arbitrary point x. Okay? And how do we determine internal responses inside beams and structures? We break out the secret weapon, which is a samurai sword or a lightsaber if we happen to be a sci-fi fan. So what I'm going to do is I'm going to take my beam and I'm going to cut a section. Okay? And I'm going to cut a section at some distance x from the origin. Okay? And I'm going to draw the free body of that. Okay? I'm going to draw the free body of that. So let's take a look at that. So here's the beam. Here's the support. I have some reaction. I'm just going to leave that as R right now, but I'll change that later. Bless you. All right. So here's my distributed load. Oh, goodness. We'll call that W. This dimension is X. And there we go. Right? So that's me literally just redrawing. You know, imagine if I cut a samurai sword and just erase that's what it would look like. Is that fair? Okay. Now, let's start off dealing with that distributed load. Remember, I don't like dealing with distributed loads when I'm summing moments. I like to collapse those into a single point load. How much is that point load? W times X. Right? Because if it was 2 kips per foot for a distance of 30 feet, it'd be 60 feet. How do you do that? You take the distributed load times the length. Okay. Now, how do we figure out, all right, let's make sure we're clear about this. What is this distance? X over 2. There we go. The last thing that we need to do is draw our unknown shear and our unknown moment according to their positive sign convention, right? And then now it's time to sum moments. And specifically what I'm going to do is I'm going to sum moments in the place that I cut. Well, let's see what I get. So I have, which is negative, I have, let's see, what do I have? I've got Wx times x over 2, which is positive, plus m is 0. I'm going to take a step back and calm down for a second, make sure that that part was clear. Is everybody okay with that? Right? So, let me scroll up a little bit to make sure that I'm not reaching too far. So I'm summing moments at the cut. So R times X is negative, Wx times X over 2 is positive, and okay, with me so far? So if I rearrange this a little bit, I get M is Rx minus W over 2x squared. Does that look right so far? Is that a quadratic? Yeah. Is the x squared term negative? Yeah. Right? So far, this is looking good. The only thing left to do is figure out, well, what the heck is R, right? Well, that's actually pretty easy, okay? if I go back up to my original beam, the two R values are the same. What are the R values? How do we determine that? WL over 2. Right? The total load, cut it in half on either end. Pretty simple. So therefore, oh, didn't mean to zoom in like that. Therefore, M of X is WL over 2 times X minus W over 2 X squared. I don't want to skip over that. I want to take my time to make sure that that part was clear. Take a sec, make sure we're clear on that. Everybody good? It's going to be very procedural, very mechanical. It's going to be a lot of alphabet soup, but it's not going to be hard. It's actually going to be pretty easy. So I don't want the alphabet soup to scare you. So we'll call it step 2, integrate twice. All right. So remember, we're saying that EI y double prime is M. Okay? What that means is that EI y double prime is WL over 2 times X minus W over 2 X squared. So therefore, how do I determine EI y single prime? Well, I need to integrate. I need to integrate all of this. Okay. These integrals are actually really easy. So, by the way, this is not a calculus. Of X, we're not doing that. Okay, so don't worry about that. These are polynomials, and that's it. So, let's carry these integrals out. Okay, so I want you to treat this as the other constant times X squared. The variable is X. Everything else is a constant. If I integrate X, what do I get? Squared over 2, right? So I have WL over 2 times X squared over 2 minus W over 2 times the integral of what? What is the integral of X squared? X cubed over 3. Is that it? Plus C. Now in this case we're going to call it C1 because we're integrating again and we're going to get a C2. So just call it C1 now. So I'm going to simplify this a little bit and I'm going to say, okay, WL over, I got 2 times 2, so we'll say 4 X squared minus W over 6 X cubed plus C1. Variables over here. So I don't like collecting it into a single fraction for this. I think it makes it a little easier to just carry it out. So here's our first integral. Now let's do the second one. So EI y is the integral of that. So now what do? I just integrate this again. Okay? So integrate it again. So let's take one step at a time. So WL over 4 times what's the integral of X squared? Minus W over 6 times what? easy integrals, right? I don't want the alphabet soup to scare you because it's really not that hard. Plus, now what do? C1x. And then, there you go. Now you see why we call them C1 and C2. So boom, this is our function for deflection, right? Let me pretty it up a little bit. So this is WL over 12 minus W over 24 plus C1x plus C2. So good? Okay. Now, step 3. Boundary conditions to solve for C1 and C2. So C1 and C2 are arbitrary constants of integration based on this problem. Okay? So we need to know what those boundary conditions are. So I'm going to scroll up a little bit, is that okay? So here's the beam. What can you tell me? So what we're trying to do, let's be clear, what we're trying to do is determine a function for deflection. Here's the beam. What does it look like when it's deflected? Maybe, I don't know, something like that, right? This is y. That's the y of x function that we're trying to determine. Are there any values on the function? No? What are they? The deflection at A and B are 0. Now, what are the x coordinates at A and B? X equals 0 and x equals L. Okay, so those are our boundary conditions. Okay, here are our boundary conditions. So boundary condition 1, y at 0 is 0. Boundary condition 2, y at L is 0. Those are the boundary conditions. We're going to have a cantilever beam next, and it'll have different boundary conditions. So we'll also maybe come up with a little shortcut on doing that problem. One at a time. I like dealing with zeros first. Zeros are easy to deal with. So let's deal with BC1 first. So y of 0 is 0. Okay, well, what do we know? We know that EIY is WL over 12x cubed minus W over 24x to the 4th plus C1x plus C2. So what do? We plug in x equals 0 and y equals 0 and solve. So EI times 0, WL over 12 times 0 to the third, minus W over 24, 0 to the 4th, plus C1 times 0, plus C2, just C2. Equals 0 minus 0 plus 0 plus C2. So, hey, that one's easy. And that happens. That's common that one of them is 0. Okay? Now the other one is not going to be 0, but we'll see what happens. So BC2. Y of L is 0. So now, here's our function. EIY is WL 12x to the third minus w over 24 plus c1x. I'm not even going to bother writing c2 because I know c2 is 0, right? So what do? EI times 0 is WL over 12 times L to the third minus W, oh, see, I forgot something. That's x to the fourth plus C1x. So W over 24, L to the fourth plus C1 times L. Y'all see what I did? Okay. So 0 over here equals, now watch what I'm going to do. Hey, look what I've got. I've got pretty much, yeah. You'll see what happens. Yeah, so we have W, well, it's not WL to the fourth, but you're kind of on the right track. So WL to the fourth over 12 minus WL, that is WL to the fourth, and that is 1 over 12 minus 1 over 24 plus C1 times L. Y'all see what I did there? And what is 1/12 minus 1/24? 1/24. So I get 0 equals WL to the fourth over 24 plus C1L. Subtract negative C1L is WL to the fourth over 24. So C1 is negative WL to the third over 24. What do you think? So far, so good? Okay. I'm going to take a second. I see some folks still writing, so we're going to take our time on this. So far, so good? Okay. So if you want, EIY is WL over 12 x to the third minus W over 24 x to the fourth plus C1x. C1 is negative WL to the third over 24 times x. And then if we want, we can say y of x is now WL over 12 EI x to the third minus W over 24 EI x to the fourth minus WL to the third over 24 EI times dividing both sides. Okay? One thing that's also kind of valuable if you want is, so for one, we could factor this a little bit, and I'll show you what would happen if we did factor it. I'm going to hold off on factoring it just now. But I'm also going to go ahead and develop an EI. Excuse me, my pen got wrangled up. An EIY prime. EIY prime, when we did that, it was WL to the fourth x squared minus W over 6x to the third plus C1, which is that y prime of x is WL over 4x squared minus W over 6x to the third minus WL to the third over 24. So, to be clear, this is an answer right there. That's the deflection as a function of x. Oh, sorry. Oh, hold on. Forgot my EIs. Right there. Now, if you open it up to the back of the book, the answer in the back of the book is going to look a little different. The only reason it looks different is because it's factored. That's the only reason. And I'll show you that in the end. But I kind of want to hold off on factoring because I want to get to maximum deflections. And I actually think it's easier to deal with maximum deflections if you sort of leave it like this. I'm going to stop for a second, make sure everybody's good with this so far. So good? Okay, now, this will tell me what the deflection is as a function of x, what the slope is as a function of x. Now, you can test this to see if it works. Does it derivative of this? X cubed, the derivative of x squared, so 3 over 12 is 4, right? X to the fourth, derivative of a fourth is 4x to the third. And then this just becomes that. So it passes the derivative test, but I'm an engineer. It's great to find the deflection as a function of x, but I want the worst case scenario. I want the maximum deflection, right? Okay. Furthest from any supports. So, okay, all right. So you're basically saying that because the problem is symmetric, maximum deflection is in the middle. That is 100% correct for this problem.
On the highest moment, or the area with, or the point of the highest moment.
Hold on. It's simpler than that. Where is a function maximized? Derivative is 0, right? So if we take this equation, set it equal to 0, and solve for x, we will determine the x coordinate to plug in here. To do that, but you will have to do that on your homework. It's a lot easier on your homework because the homework has it's a simpler function at the end. It's much simpler. But I just want to make sure that that's clear. All right. So to be clear, for determine Ymax, so we'll say set y prime equals 0, solve for x, plug that x into y to determine Ymax. But note by observation Ymax occurs at x equals what? L over 2. So let's see what that is. Ymax is y at L over 2, which is, so I'm taking this upper equation, so WL over 12EI times L over 2 cubed minus W over 24EI L over 4, sorry, L over 2 to the 4. Minus WL to the third, 24EI, L over 2. All right, so let's see what that does. So, WL to the fourth over EI. And then what am I going to have? I'm going to have 1 over 12 times 1 over 8. Is that right? Y'all see that? So minus WL to the 4th over EI. What am I going to have here? 1 over 24 times 1 over 16. Y'all see that? Because, so like for here, this is the 24, and then L over 2 to the 4th. 2 to the 4th is 16. I've got 4 times 116. With me so far? And then over here, so it was at 196 minus 1, what is that, 384th? How did I do? Did I do that right? Let's see, hold on, breaking out my calculator. 24 times 16. $384. Yeah. Minus 1 over 48. Does anybody have a Casio FX 115ES Plus and tell select these together?
Pretty good.
Well, pi equals E equals 3, take it or leave it, right?
1 over 48 minus 1 over 384.
Oh. Casio FX 115ES Plus. Anybody got an answer?
Negative 5 over 384.
So negative 5 WL to the 4th over 384 EI. Is that right? Well, let's see. Maximum deflection. 5 load L to the 4th over 384 EI. Well, by golly gosh gee, look at that. The reason for the negative, just so you are aware, well, yeah, because we're assuming downward deflection. So if you want positive deflection, what you could have done at the very beginning is instead of saying EI y double prime equals M, you could say EI y double prime equals negative M, and then it would have all got washed out. I don't think it really matters. We know the beam's deflecting downward.
Yeah, flip your axes.
You can do that too, you know. It doesn't really matter. But does that make sense? So I don't think this is that hard, right? We don't. I mean, integrate twice, use your boundary conditions, plug and chug, simplify. Now, since we're engineers and we've lived too far into letters land, let's do some numbers. Okay? All right, so note. Given W is 2 kips per foot, L is 30 feet, E is what? What were we given? 29,000 KSI. And I, 1,500 inches to the 4th. Is that right? So, right? 5 WL to the 4th over 384 EI. But does everybody see a problem? the units don't work out, right? These are in feet, these are in inches, but I seem to remember that we derived a very magic unit conversion factor that would get everything into a consistent unit system and yield units, or yield an expression with inches. So what is that? Check that out. Potassium FX 115 ES plus should just be by instinct. They have a value for me on that?
0.838 inches.
There we go. Yeah, so at the end of the day, we derive very, nice and neat plug and chug equations. As long as we convert our units properly, it's pretty straightforward. So, if we wanted to determine maximum rotations, where would maximum rotation be? Where would maximum slope be? In other words, here's the beam, right? Here's the beam. Where is maximum rotation? Where's the maximum y prime? Well, shape. Where does the shape have the biggest slope? The supports, right? They're going to be equal, right? Now, I'm lazy. I don't know about you, but what do you think is easier to plug in right here? X equals 0 or x equals L? 0. If I plug in x equals 0 to this expression, what do I get? 0 squared, 0 cubed. I'm just left with this term right here, this WL to the third over 24 EI, right? What did the PowerPoint yield? WL to the third over 24 EI. By golly gosh gee, right? Pen's connected to the, I can't drop on, pen drop on the desk. Make sense? And so all I would have to do is this similar conversion, like I'd have to do a similar plug and chug for rotations, only instead of 1728, I'd use 144 times 1. If you do that, I'll go ahead and tell you, after computations, y prime max is 0.427 degrees. You ought to try that out. It's not hard, but all right, any questions? I want to try and do another one real quick. This one's going to be a lot kinder on the symbolic slant, okay? I told you we were going to have some alphabet soup today, so. Any questions? All right, let's do the next one. Because it is a cantilevered beam. I wanted to do one that has different boundary conditions. Now, and I want to see if we can come up with a simpler way of assessing this because we have a cantilevered support. Cantilevered supports afford us a little bit of an easier way of assessing the deflection, if you will. Now, another thing about this problem is this problem is going to be a little bit more numeric, okay? What I mean by the numerics is nothing but symbols. I'm actually going to have numbers in my functions. It'll make it a little easier, make it a little bit more straightforward through the math. The only downside is that the functions that we derive are really only going to work for this problem. They're not going to work for, if I were to change it to a 50-foot long beam with a load of 25 kips as opposed to 10 kips. Like if I change the numbers, I'd have to do the analysis again. That's a big deal for this type of problem. Okay, let's see if we can conceptualize what do we think the shear diagram is going to look like for this beam, right? It's going to go down, over, up, right? So if we have a constant shear diagram, what's our moment diagram going to look like? Right? And is it going to go down like that? Hold on, let's see. Let's see, what is our reaction here? That's 10 kips, right? What's our moment reaction? We have 10 times 24 this way, 10 times 24 this way, so this is 240 foot kips that way, right? So, shear diagram, we go down, over, up, so negative 10, 0, 0, that's our shear diagram. The area under here is minus 240. So for our moment diagram, we start at 0, drop down to negative 240, and then that concentrated moment brings us back up. Isn't that right? So, having m of x, we know this is linear. Of m of x. Well, how do we determine the slope of a moment diagram? Maybe we look at the shear diagram. Right? The slope of the moment diagram is the value of the shear diagram. Moment diagram. Here's my coordinate system right here. Where does this moment function? Because this line right here, to be clear, this line, that's that. Here's my y-axis. There's my x-axis. What's the y-intercept? 0. Boom. That's it. If you don't believe me, we can cut a section. We can draw the beam. We can say this is 10 kips. This is x. We have an unknown shear, an unknown moment. We can sum moments and we will find 10x is this way, m is this way, m is negative 10x. It's the same thing, right? With me so far? Now, before we start integrating, I want to see if we can identify the boundary conditions. This. All right. I want this to not be cluttered. Being clamped on the right end and it's being deflected downwards. So if I conceptualize what this deflection looks like, it's going to look something about like that. Maybe I don't know. Oh, little button here on the pen. Maybe something like this. Is that fair? What are the boundary conditions then? First off, I mean, our known point where we know the deflections is over here on the right. What's that? 24, right? The 24, it's over on the end. Over here is 0. What else is 0 over here? The slope. So I propose that my two boundary conditions are y prime of 24 is 0 and y of 24 is 0. That's different than before, where we had deflection on the right end is 0 and deflection on the left end is 0. We're dealing with a clamped support. The whole point of a fixed support is that it restrains moment. If it restrains moment, it restrains rotation, right? If it fully restrains moment, it fully restrains rotation. That's what I'm going to say. Now, there's a reason that I wrote it in this order. That I wrote the derivative first. I wrote y prime first and this one second. And you'll see why here in a second. All right. Is everybody with me so far? Okay. So let's integrate twice. So EI y double prime is negative 10x. So EI y prime is the integral of that. What's that? What's the integral of x? Yeah, so negative 5x squared plus c1, right? Go ahead and do right now. Shaking your head, yes. What can we do?
Plug in the y prime value to get c1.
We could go ahead and solve for c1 now, right? We couldn't do that before. We couldn't do that before with boundary conditions that only related to the function. But because we're dealing with boundary conditions that relate to y prime, we can go ahead and solve for c1 right now, okay? So let's go ahead and do it. Let's go ahead and apply boundary condition 1. So right? So y prime of 24 is 0. So EI y prime is negative 5x squared plus c1. So 0 is negative 5 times 24 squared plus c1. 0 equals, okay, so what is that? I'm not that good. So negative 2880 plus C1. C1 is 2880. So this equals negative 5x squared plus 2880. We can go ahead and just do that now, you know, make it a lot easier on us. Now, we can do EIY. Everybody good so far? Any questions? Here, we'll put this down here. Now, a lot of times you find cantilever beams are actually a little easier. So integrating twice, so here's our second integral. What's the integral here? X squared, integral of x squared is x cubed over 3. So negative 5 plus, now what do I do here? What's the integral of 2880? Yep. Plus, we'll call it C2. And now we have our second boundary condition. So plug in y is 0. All right, so let's see. So 5 divided by 3 times 24 to the third. I'm getting negative 23,040 plus this is 69,120, right? So if I look at this, C2's got to be negative, and it's got to be the difference of those two. So C2 is 46,080, right? Okay, nope, that's negative. Boom. I'll show you what Ymax is here in a second. It's actually really easy. But this one, we were able to compact our calculations a little bit more because where the boundary conditions related to both the derivative and the function, we were able to sort of handle them as we went on. Made the math a little easier. I mean, we could have applied them all here, but I mean, we could have like done the analysis and then applied it here, but then I think it would just been more steps to get the same answer. So I don't have a specific way of doing it. I'm just the simplest way. Got it. Okay. Some people did. Real quick, how do we determine maximum deflection? Well, where is maximum deflection on this beam? At x equals 0, right at the free end. So if x equals 0, that's 0, that's 0, maximum deflection is just this over EI, right? So if I wanted to determine maximum deflection, where's maximum slope, by the way? X equals 0, right? Same place. So let's do both. Hold on. So y prime max, and in some of the places in the textbook that might be called theta max. So that's sort of the same thing. So it's going to be y prime at x equals 0. It's just going to be 2880 over EI. So 2880, and I think for this problem we were given that E was 4,000 KSI, and this is 8,000 inches to the fourth, and we have our magic conversion factor that will get our answer in degrees. And then for Ymax, which is sometimes called in the textbook delta max. So if you see delta max, that's the same thing. So it's just y of 0, in this case negative 46,080 over EI. Again, different unit conversion factor, but sort of the same magic. Answers in inches, answers in degrees. And so you're going to do for the top 2880 times 144 times 180, 184,000 times 8,000 times pi. I'll go ahead and tell you, when you chug that out, you get 0.743 degrees. Then for this one, you get 2.488 inches. Well, there was a lot of alphabet soup this morning. My apologies.
Do you know what class we're going
What did you say?
to? Do you know what class we're going to next?
You never seen any alphabet soup before? No. What's that?
You ever calculate?
I with some of this stuff. One thing I do want to say on your homework assignment that's due Thursday. So I want everybody to listen. So there is a case in the back of the book that will serve as a check. But I'll tell you something, all right? So the problem for your homework is a beam, and there's a concentrated moment on one end. Okay. Now, in the back of the book, the moment is on this side. On your homework, the moment's on this side. Okay? Now, the reason for doing that is it makes this part a lot easier. Okay? So I did that on purpose to make your life easier. I also plotted the shear and moment diagrams for you to, again, make that part a lot easier. Okay? Done correctly, however, the maximum deflection that you get for your homework problem should be the same as what's in the back of the book. But here's again, maximum deflection for the beam on the homework does not occur at L over 2. Okay? You have to take the derivative, set 0, solve. Okay? It's not going to be, I'm saying again, it's not going to be at L over 2. With me on that? That will make your life hopefully a little easier. Now I'll let you go. I will see you all on Thursday.